Hello. Today we'll look at another area of numerical analysis. We will again work with matrices, and this time we will ask about eigenthings, by which I mean eigenvalues and eigenvectors, which is something that we know from linear algebra. Now I put up the formal definition to remind us of it, and it all boils down to the following thing. We have a matrix, and we are looking for a vector and a number, so that the following equality works. Now, in linear algebra, they also told us how to find them. First, we find lambda, and then we find a corresponding eigenvector v. Now, this procedure actually works, and we did some calculations by hand, and we got the right answers, so it actually seems that we do have a numerical method. However, it's not very practical when it comes to larger matrices, and we know that in applications, we do have large matrices very often. So just imagine that you have a matrix, let's say 1000 by 1000, which is actually a rather small matrix. And you try to follow the linear algebra procedure. So first you need to find eigenvalues, so you create the characteristic polynomial, which will have degree 1000. Now finding roots of a polynomial of degree 1000, that's a big problem because there are no formulas for that. So you may say, okay, we had some lectures previously on numerical methods for finding roots of functions. So we apply, for instance, the Newton method, and we get an approximation of some eigenvalue. So far, so good. Then comes the second step. To find the associated eigenvector, in linear algebra, they told us to solve a certain system of linear equations, which was homogeneous, and we were looking for a non-trivial solution. So the system had to be singular, with infinitely many solutions. And this works if you use the precise value of the eigenvalue. But if you use an approximation of eigenvalue instead, then it's very likely that the system which will be created like that is actually regular, and that's the end of the road. This cannot be fixed. That's fatal. So this procedure, which worked really well at school and it works really well for small matrices, it's actually not very flexible. We need to find something else. And for that, we need to change the point of view. In linear algebra, we went first lambda, then v. And now we will reverse the point of view. So we will look at this equation and we will think, okay, we know a, and now let's assume that we also know lambda, which is a very optimistic assumption, perhaps bordering on naivety, even foolishness. But let's roll with it for a few minutes and we will see where it gets us. So we know a, we know lambda, perhaps, and suddenly it's just a single equation with single unknown, which is a fairly nice situation. And when we were talking about solving equations, I was praising the fixed point approach for being really flexible, adaptable to many settings. Okay, here we have an equation, and the unknown is actually a vector, so we cannot use bisection, things like that, but the fixed point approach could work. Let's try it. We are supposed to isolate v from this equation, and it's much easier to isolate it from the right-hand side. So I just divide by lambda, and I get v is 1 over lambda av. And that's the key equation. Now, what if lambda is 0? Well, if lambda is 0, then the matrix A itself is singular, and this is not really a problem in application, so we do not have to really worry about it. And after all, if lambda is 0, then we know it. So that's a nice situation. So let's assume that lambda is not 0. Let's not worry about it in this talk at all. So we have an equation. It's a fixed point type of equation. So on the right, there is a mapping. And this mapping defines an iteration. How does it go? Well, we just choose some x0, a vector of appropriate dimension. The dimension is given by the dimension of the matrix A. And then we just introduce a recursive formula or iterative formula. The new generation of a vector is obtained by taking 1 over lambda, a, and the current generation. So that's the key iterative formula. Now, what are the chances of success of this iteration? That's a good question. Now, we investigated convergence for this iteration before, and we actually used some interesting tools like contraction, the Banach fixed point theorem. Unfortunately, that's not going to help here, because when we look at the mapping, which is defined by this formula, it turns out that it's actually not a contraction typically. So we are out of luck. And if you want to get some information on convergence, we have to actually look into the mechanics. which is happening here into the calculations using tools of linear algebra. And for that, we will need some assumptions. Let's have a look at the first one. We will assume that the eigenvectors that exist, Vi, actually form a basis of the space Rn, where n is the dimension of the matrix. So that's the first assumption. And a good question is how restrictive it is. And actually, it is quite restrictive, but on the other hand, there is an optimistic news, which comes from the good people from linear algebra. And it is a nice fact which says if you have a matrix which is real and symmetric, then you have real eigenvalues, which is convenient. And more importantly, the eigenvectors form a basis. And in applications, many matrices are real and symmetric, so this is wonderful. For those matrices, this assumption is true. On the other hand, there are some really cute and nice matrices that are not symmetric. It actually turns out, and we will see it later on, that this assumption is not crucial, it's more like a convenience for me. With this assumption, I can do some easy calculations, some easy proofs, so this will be okay. But later on, I will not be all that big on it, so we don't have to worry. Okay, we have a basis. We have initial vector for our iteration. What does it mean? Well, I can write it as a linear combination of the basic vectors. Alpha I, Vi. Alpha I are some real numbers. Vi are the eigenvectors. And the summation runs through 1 to n. N is the dimension of the space. Now I start iterating. From x0, I get x1. How does it look like? Well, it's 1 over lambda a x0, which is 1 over lambda a summation alpha I Vi. Okay, what will happen now? Good question. 1 over lambda. And now, this is actually a series of multiplications. There are some matrices, some vectors involved, and for that we do not have commutativity, but we do have, for instance, the distributive law. So I can actually move the matrix A inside, or in other words, I can pull the summation outside, and the matrix now appears here. And there is a rule which says if you have some real numbers or complex numbers, whatever, some scalars in such a chain of multiplications, you can pull them out. So I'm also pulling out alpha I, and this matrix A eventually filters through to this position in front of the vector Vi. And there we cannot switch anymore. That's the point where commutativity does not work. But I look at it and I actually sort of enjoy this form because I'm thinking, okay, A is a matrix and Vi, every Vi is its eigenvector. So A times Vi, that's just lambda I Vi. Lambdas are the corresponding eigenvalues. Okay, so that's x1. And when I compare it with x0, I can see some changes. Let's try x2. Well, x2 is 1 over lambda a x1. Now we substitute. I forgot 1 over lambda. Okay, got too hasty. Alpha I, lambda I, Vi. So I substituted for x1, and now again I'm going to take a and move it to the right as much as possible. 1 over lambda, that's a constant, and it can move out of this chain of multiplications. Then there is a summation. I'm also pulling out alpha I, these are numbers. Lambda I, these are numbers. And that's the place where the matrix A finishes, in front of the vectors Vi. And the same argument applies. So we get 1 over lambda square, summation, alpha I, lambda I. And now there is another lambda I coming from this product. So it will be lambda I squared, Vi. And that's formula for x2 that I wanted to see. And again we compare. Do we see the pattern? Well, with every iteration, there will be an extra lambda in the denominator, which is not surprising because we can see it over here in the formula. With every iteration, we divide by lambda. And with every iteration, we multiply by the matrix. And this multiplication always bubbles all the way to the back and creates an extra power of lambda I, of the eigenvalues. So I think it will not be really controversial if I claim that the kth iteration looks like 1 over lambda to power k, summation I ranging from 1 to n, alpha I, lambda I to power k, vi. And indeed, it just takes a few lines to actually prove by induction that this formula is true. So we know how the iterates look like, how the sequence of vectors develops. And a good question is, what happens when k goes to infinity? And for that, I'm going to write it in a slightly different way. Xk is, and I'm going to take 1 over lambda to power k and move it here, connect it in the sum with the other guys, with lambdas I. So the summation, the alphas, the coefficients, alpha i's, and now the lambdas, I put them together and connect them into one power, like that. So it's lambda I over lambda, that all to power k, and the eigenvectors vi. Now let's imagine what happens when we send k to infinity. Well, the only place where the k is over here, in the exponent. In fact, these are geometric sequences. Notice also, and it's important, that the range of the sum does not change as we are moving k. There is a fixed number of terms which are summed up, and each term has this form, so in each term there is this geometric sequence changing and the rest remains the same as we are changing k. And that's an important moment. What do we know about geometric sequences? Everything depends on the base. If the base is larger than 1, then such a sequence goes to infinity, and we do not want that. And if the base is smaller than -1, then in absolute value it goes to infinity. It oscillates wildly, actually. So we do not want that. So we have a strong motivation, and this is where it gets interesting, to choose lambda in such a way that all these geometric sequences do not go to infinity. They do not cause troubles. Now, remember, lambda is supposed to be an eigenvalue. So we are choosing some eigenvalue, fixed eigenvalue lambda, and then in the sum we are comparing it with all eigenvalues. And we do not want these numbers to be larger than 1 in absolute value. What does it mean? Well, it means that we have to actually choose for lambda the largest eigenvalue of them all. And only then we have a chance of getting some nice convergence out of it. So there is assumption number 2. We order lambdas according to their magnitude, and the largest guy will be called lambda 1. And the second largest will be called lambda 2. And so on. And there is n lambdas, n eigenvalues for a matrix of dimension n, if we also include them according to their multiplicity. Now, how restrictive is this? Actually, is this a restrictive assumption? When I get numbers, I can always order them by their magnitude. Well, we have a sharp inequality here, not anywhere else, but here we have a sharp inequality, and that is a restrictive assumption. It may happen for a matrix that you have two distinct eigenvalues with the same magnitude, and they are in trouble. This assumption will no longer work for you. Or perhaps you have an eigenvalue which is the largest one, but it has larger multiplicity than 1. So there's actually several copies of this eigenvalue here in this list. And again, they are all of the same magnitude and they are the largest, so this sharp inequality would not work. So this is a restrictive assumption. And unlike the first one, it will stay. We will not be able to get rid of it. That's a substantial, crucial assumption, okay? So having this assumption, I decide to do these iterations for lambda 1. So lambda will be lambda 1 now. And with this choice, let's have a look at all these terms. They now fall into two categories. When I is equal to 1, so for the first term in this sum, we have lambda 1 in the denominator and also lambda 1 in the numerator. So this sequence is actually just 1 to k, which goes to 1. So with the first term, this looks great. Let's have a look at the other terms. Here, I is greater than 1. And then in the denominator, we have lambda 1, which is the single largest eigenvalue. And here in the numerator, we have something smaller. So the absolute value of lambda I over lambda is definitely smaller than 1. And therefore, the geometric sequence, which has this as a base, converges to 0. So let's wrap it up. We decided to try iteration like that, where lambda is the single largest eigenvalue. We get a sequence of vectors, and we ask, what happens with those vectors when we send k to infinity? And we look at those terms, and we notice that in the first term, this middle part goes to 1, and these other parts are constant. So this term as a whole converges to alpha 1 v1. And then we look at the other terms in the sum, and we notice that these two terms are constant in every part, and the middle part goes to 0, and therefore this whole thing disappears, and that's it. We just proved that our sequence of vectors converges to a vector v1 alpha 1. Now, what is this vector? v1 is eigenvector associated with lambda 1. If you multiply it by a constant, that's just another eigenvector. Let's call it w1. And that's the happy end. If we apply our iteration, then we just mathematically proved that after, under some assumptions, we do get convergence, we do get the corresponding eigenvector. Or perhaps not. In mathematics, when we do general statements, we should always worry about some assumptions that we sort of overlooked or forgot. Is it really true that when you take an eigenvector and multiply it by a number, you get another eigenvector? Yes, it is true, assuming that this number is not 0. So that's the third assumption. Alpha 1 should be different from 0. And now, this assumption has nothing to do with the matrix. It has something to do and everything to do with our choice of the initial vector. If we want to find the eigenvector associated with lambda 1, we have to make sure that the direction v1 is present in the decomposition of x0. How can we arrange for that? The answer is we can't, because we do not know this direction v1. So this is a little complication, but it's not a problem. I'm not going to call it a problem. It's a complication. What happens if we choose randomly a vector and v1 is not present there? Then essentially this whole direction and this whole world of lambda 1 disappears from the calculation, and the second largest eigenvalue gets promoted, and we obtain the eigenvector for the second largest eigenvalue, which is not a tragedy, okay, but we should be aware of the fact that when we do, okay, I will show a little, let's say, improvement on the scheme, and we will get some iteration. It will provide us with eigenvector, eigenvalue, and we should be aware of the fact that this eigenvalue need not be the largest one if we were unlucky with the choice of the initial vector. So what we do in applications actually in real life is that we try some initial vector and we run it and we get some eigenvalue, which could be the largest one or perhaps not. So we try a different initial vector in a different direction and perhaps another. And if we keep getting the same eigenvalue, then most likely by taking different initial vectors, we actually covered all the possibilities, and yes, we do have the largest guy. Okay, so this is not really a problem, just a little complication. Okay, we have a nice procedure. We have shown mathematically that it works. So it seems that we are done, but we are not done, because imagine that you are actually doing this iteration. So you start with x0, you multiply it by matrix A, no problem. You divide by lambda. Where is lambda? Well, this lambda here, that's our dose of optimism, which just ran out. So that's a problem. That is a problem. How do we solve it? By another dose of optimism. Let's have a look at it. I have my vectors in my iteration, and optimistically, I'm going to assume now that after a few rounds of this iteration, I got really close to my eigenvector. Then if I apply matrix A to my vector, then hopefully, because I'm almost at the eigenvector, this should be really close to lambda 1 xk. Hopefully. Now I apply a norm, any norm that I feel like. In numerical analysis, we actually really like the infinity norm or the row norm, but I may have reasons for using other norm, for instance, the Euclidean norm. Why not? Okay, so there is some norm here, applied on the left and also on the right. Now we had some identities for the norm. On the left, well, we actually had some identity also for this matrix multiplication, but I'm not going to use it. I'm going to use the identity for multiplication by a scalar. And this scalar can be pulled out in absolute value. And I get a formula which allows me to approximate my eigenvalue lambda 1. Lambda 1 could be, let's see, the norm of axk and the norm of xk in the denominator. Okay, that's a nice formula, where on the right-hand side I know everything when I'm at the stage k of my iteration. So that's wonderful. I have my approximation, and I can use this approximation in my iterative formula. So let's have a look how this iterative formula looks like now. To obtain xk plus 1, we would want to use 1 over this estimate. So it's the norm of xk divided by the norm of axk times axk. And that's it. Now, there's actually a nice thing that axk, I need to calculate it here, and when I calculate it, I can use it here right away, so this is not too much work. So that's not really a bad formula, but still, it can be made even slightly simpler. How will it look like if the vector xk had norm 1? The answer is a little bit nicer. Let's put it here. That's the iteration that I want to use, actually. Xk plus 1 will be just axk divided by the norm of this new vector. Good question is, I can use this formula if the vector xk has norm 1. Can I do it? Well, let's see. With the vector x0, the initial vector, I choose it randomly, let's say, but then I can always divide it by its norm, and then I get a new vector in the same direction but with norm 1. So we so-called normalize it. So this is no problem. So the vector x0 now has norm 1, and therefore instead of this formula, I'm entitled to use this nice formula to obtain vector x1. Vector x1 is obtained in this way. There is some vector divided by the norm of the same vector. So the resulting vector, this whole thing, again has norm 1. Vector x1 has a norm 1. So to get x2, instead of the complicated formula, I can use this formula, which makes vector x2 again of norm 1 and so on. So this formula actually serves two purposes. It normalizes vectors, and therefore it justifies that this simplified formula can be used instead of this one. It's like a magic. It all fits together beautifully. This is a very nice iteration, and it does work. Let's have a look at it. Okay, we have a 2x2 matrix, which is not symmetric. So we are not really quite sure whether the eigenvectors that we have form a basis or not. But as I commented, this assumption is not all that crucial. Let's use this iteration, which is, by the way, called power iteration. I will get to it soon. And I'm applying it with the initial vector 1, 3. Why did I choose it? I don't know. Probably because it reminds me of 13. Whatever. And I'm using a method which I call normalized. This is normalized iteration because we just normalize. We don't do anything more. And let's see what we get. Bang. 12 iterations. What do we see on the left? On the left we see vectors. These are the xk's. And they all have -1 for the, or almost all of them, for the first coordinate. And this is not an accident, because remember, we are normalizing vectors, and I'm actually using the infinity norm, which is the maximum of the coordinates. So one of these two coordinates must be 1, automatically because of normalization with respect to the maximum norm. So this works here. And now for every vector x, xk if you want, I'm actually finding corresponding estimate of lambda, of the eigenvalue, using the formula that we see over there. So I'm actually estimating lambda as norm of axk. And I look at those estimates of lambda, and they seem to go to 3, which is the first number. That's the official output. And the second part, that's the official vector, which is coming out of my procedure, this W1. And now, this is a school problem. And because it's a school problem, I expect to get nice answers. So I strongly suspect that this number, the first number, is actually supposed to be 3. It's an attempt to get to 3. So perhaps 3 is an eigenvalue of my matrix. And perhaps this vector, which looks like, let's say, -1 and -1/2, should be the eigenvector. Now, we know that we can take and multiply eigenvectors by non-zero numbers. So I'm going to multiply it by -2 to get 2, 1. I am not saying that this vector is not nice. I just prefer this one, okay? No prejudice here, definitely. So let's check whether my guess is correct. I have a little code here. So 3 is my attempt or my guess for the eigenvalue, and the corresponding eigenvector could be 2, 1. And what I'm going to do now, I will look at the difference between these two expressions. You can see it over here. And each of these expressions is actually a vector. So when I subtract, I get a vector. And I sincerely hope that it will be a 0 vector. And this will confirm, and it does, that these two parts, these two sides of the equation are really truly equal. So we do have an eigenvector, eigenvalue. This really seems to work. And perhaps this is also the largest eigenvalue. But I cannot be sure because perhaps there is a larger one with eigenvector going in a different direction. So what do? I started with vector 1, 3, and I start with another one with different direction. Let's say 1, 0. That's a nice vector. So I will try 1, 0 over here, where somebody stole my cursor. Okay, here it is. 1, 0. And I get another iteration on the left, some vectors, which converge to 1, 1/2, which is just an opposite direction. So the eigenspace is really in the direction to 1. And the approximation of eigenvalue again looks like 3 to me. Yeah, that's an attempt at 3. And because I tried two different directions and we are in two-dimensional space, there can be no other direction hiding anywhere that I didn't see. So 3 is really the largest eigenvalue. And I have a confirmation. It works really nicely. Now let's put up an official slide and give it a name officially. So this is the power method for finding eigenvalues, eigenvectors. We start with some x0, and then we just recycle the formula that we can see over here. And you can see that I'm using the infinite norm for the normalization. And it does work. It's an iterative procedure, so we need to know how to stop. So in the last line, you can see the stopping condition, and it's the good old absolute difference stopping condition. So I have an iteration, I have the next one, I compare them. If they are far apart, I conclude that there is still some work to be done. But if they are almost the same, then I say, okay, that's probably already the right answer. Okay, no magic there. So that's my algorithm. And by the way, what would happen if I used a different norm? It would also work, but perhaps another norm would not be so convenient. Okay, so in numerical analysis, we really prefer infinity norm, but there are some good reasons, and we will see some soon, for using, let's say, the Euclidean norm. So just out of curiosity, here I'm again using the same power iteration with the same initial vector 1, 0 that we can see above. Everything is the same, but now I specify that I want to use the 2 norm, the Euclidean norm. And I get another run, which again gives me 3, and this is the disadvantage. There is a vector here now, which hopefully is parallel to vector 2, 1, shows in the same direction. Is that true? Is the first coordinate double of the second one? I would say yes. Yeah, so it seems to work. But it's, let's say, less convenient for interpretation. Okay, that's one of the disadvantages of using a different norm. But otherwise, it seems to work really well. How many iterations? 11. And over here, 11. So it comes to about the same thing. And perhaps, yeah, the convergence seems to be equally fast. So there is not much to choose from, really. So that seems to work. Let's try another matrix. Okay, here is a matrix which I again call A, which is a little bit unpleasant. Let me explain why. The original matrix was called A, and this guy is just minus the original A. So the new A is minus original A, the opposite matrix, so to speak. Every single entry in the matrix, the sign got switched. The same approach. I take power iteration, initial vector 1, 0, which is the one that I'm using here. I'm using infinity norm for normalization. Let's see how it performs. And it does not. Well, I didn't stop because the iteration is happy. I stopped because the maximal number of iterations was reached. There are actually several stopping conditions, and one of them is that the iteration should never be larger than 50. This can be changed. Anyway, the point is, sometimes you get into a cycle, and the computer would run infinitely long, which is not nice. So it's good to check. And it says here, after 50 iterations, things seem to be, fishy. You'd better look at it. So let me have a look at it. How about vectors? Vectors, vectors, vectors. We actually have a very nice vector, which is an eigenvector, 1, 1/2, but the iteration flip-flops between the vector and its opposite. It's just goes vector, the opposite vector, vector, opposite vector. It's a cycle of length 2. So what's really happening? Let me explain. I actually cheated. I cheated in a major way, but I tried to cover it up so that you wouldn't notice. But perhaps you did. What did I do? Let me go back here. Here is the formula for iteration that I want to use. And I have a problem with this lambda. Where do I get it? So I found a formula for lambda. But it's not a formula for lambda. It's a formula for the absolute value of lambda. So if the largest eigenvalue is positive, then I can actually use the formula and everything works out, which is exactly the case of my first example. But now in this second example, when I'm taking the opposite matrix, then also the eigenvalues change sign, and therefore the largest eigenvalue is not 3, it's -3. And that's something that this procedure does not see. It sees the magnitude, but it misses the sign. So in this formula, as I'm iterating, properly there should be an extra sign minus, changing the vectors to their opposites, and then this iteration would work really nicely, but this minus sign is missing there, or in another way, there is an extra minus, and this extra minus in the formula flip-flops those vectors. That's really bad. So, 2 news. First of all, the power iteration only works if the largest eigenvalue is positive, which is a big restriction, very unpleasant. On the other hand, in many real-life problems, you have some information from that problem itself that tells you that the largest eigenvalue is unique. You also need that. And moreover, that the largest eigenvalue is positive. And if you do have this information, then this power iteration will work for you. And the advantage is that it's very simple. So this method is actually used in applications in real life, and it's used quite a lot. In many cases, this is the best way to go for the eigenvalue, eigenvector. But still, there is this problem. What do I do if I have a matrix and I know nothing about its eigenvalues? Then I cannot really use this procedure, because what if lambda 1 is negative? And this all boils down to the problem of estimating lambda, estimating eigenvalue if you know the eigenvector, at least approximately. And to solve this problem, we will use the usual trick. We will simply click. So let me click about twice. And we have a definition here. It says if you have a vector, just any vector, you can always create an expression with this vector, and it's a number. The outcome is a number. We will talk about it. And this is called the Rayleigh quotient. And why is this Rayleigh quotient interesting? Well, first of all, if your vector happens to be an eigenvector, then the Rayleigh quotient actually provides the exact eigenvalue. Let's have a look at it. Proof. We have this expression. We take the vector x and take the transpose of it. By the way, this is the version for real valued lambdas. For complex lambdas, instead of transpose, one has to take the Hermitian. Well, it's a little bit complicated, but not too much. Okay, so this is a real world version. So the transpose of x multiplies ax, and in denominator, the transpose of x multiplies x. Now, before we look how much it is, let's look what kind of an animal is it. In the denominator, x is a vector, and in theory, it's always column vector. And this is multiplied by its transpose. Let's forget for a second that it's the same guy. Let's imagine x and y. So you can see the vector x as a row vector, x1, x2, x3, x4, and the vector y as a column vector. And this is the usual matrix multiplication, the one that goes zoom, 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 the usual stuff. Here it is easy. There is just one way to do it. You simply go by the row, you go by the column, and what you get is a number. So the denominator is a number. What number? Well, you are multiplying the first coordinates, plus you are multiplying the second coordinates, third, so on. That's the dot product, or the inner product. So in our case, for two x's, this is the x vector dot product x vector. And this, in turn, is actually equal to the Euclidean norm of the vector x squared. So if you want to use this formula, in the denominator, you actually have the norm, the Euclidean norm squared, so perhaps it's a good idea to use the Euclidean norm instead of the infinity norm in your iteration. And some people do. Okay, that's the denominator. But now we know that it makes sense, but we will not use it. Let's just copy it. In the numerator, again, matrix times a vector is just a vector, column vector, multiplied by a row vector. Again, that's actually dot product. It provides us with a number. What number? I have this transposed vector, and A is a matrix, and X is its eigenvector. That's the assumption here in the last line. So the outcome is actually lambda times X. Now we can take lambda, pull it out, and when we look at it, to our pleasant surprise, we can see that we can cancel in this ratio, in this fraction, and we get just lambda. That's the end of the proof. That was a very nice proof. So this is what happens when you have an eigenvector. What if you have an approximation of eigenvector? Then the Rayleigh quotient does something else for you. But let's talk about it for a second. Let's talk about eigenvectors. Eigenvector and eigenvalue have this property, which can be written as AV minus lambda V is zero vector. And now if we fix eigenvector and we just start changing this number, so it becomes like a problem of catching the right situation. You have a vector here, so AV, that's a fixed vector. Here's another fixed vector, and you're multiplying it by different numbers and trying to match these two guys so that they are the same. You are trying different lambdas, and finally they are the same, and that's our eigenvalue. I can take the norm here, any norm, I don't care, could be the infinity norm. And infinity norm of a zero vector is 0. Now, the trick is that the norm is always positive or 0, never negative. So this is actually the smallest achievable value. And we know that if you have an eigenvector, then there is a special number which, if you put it here, you do get this 0, this smallest possible value. What happens if you have some other vector? Then AX is again a vector. It's sitting here in space, and you can actually calculate it. You can see it. And then you take this vector x and you start multiplying this vector by all kinds of numbers and looking at the difference, looking through the eyes of the norm. Sometimes they are far apart, sometimes they are close. And again, these possible values for different values of alpha have the smallest one. Smallest value means that this vector and this vector are as close as possible. And the smallest, the closest situation appears exactly when alpha is the Rayleigh quotient. So the Rayleigh quotient provides us with the best guess at the eigenvalue, which makes a lot of sense. I'm not going to prove that the Rayleigh quotient actually minimizes this expression. That's a lot of work, difficult proof. But it tells us what to do. Let's have a look at our next generation iteration. It goes like that. We have a vector xk. With the vector xk, we can find an estimate lambda k for the eigenvalue, and we find it using the Rayleigh quotient. So there's this formula, xk transpose A, xk transpose xk, whatever, Rayleigh quotient. And then we use it here in this formula to get the next generation. 1 over lambda k axk. By the way, you can notice that axk can be recycled from the Rayleigh quotient. So the Rayleigh quotient is not all that much work extra. And this will not be xk plus 1, but this will be a temporary vector, let's call it y. And then I normalize this vector and I get xk plus 1. Why am I normalizing? If I don't want to do this trick with simplification, I don't really need to normalize. But it's customary to do so because it makes the answer nicer and it prevents some problems, some numerical problems. It may happen that your vectors actually run away in magnitude or get too small, things like that. You don't want those complications. So by normalizing, you get nice eigenvectors. If you normalize with respect to the infinity norm, then at least one coordinate of your limit should be 1, which is nice. Okay? But as we saw, we can use, for instance, the Euclidean norm. And it makes sense because if you are normalizing with respect to Euclidean norm, then the norm here will be 1, and you actually don't have to bother dividing, which is also nice. So some people use the Euclidean norm, some people use the infinity norm, whatever. Okay? So this box as a new type of iteration, and here we were not cheating. The Rayleigh quotient really does estimate the lambda, so it should work also for negative lambdas. Before we try it, let me just make another click. And this is the power method. People also call it the power method. So the previous one I call normalized power method because I'm just normalizing, and some people call this the Rayleigh power method to emphasize that they're using the Rayleigh quotient. And it goes exactly the way that we expect. I start with some x naught, a vector, initial vector, and I calculate L naught, which is the initial estimate for lambda. And then I just recycle. So that's exactly what I've been explaining here. Again, here I'm choosing the infinity norm, and there is the familiar stopping condition. But as an alternative, I'm offering that you can use, if you want, also the Euclidean norm for normalization. And then for the lambda, for the Rayleigh quotient, you have a nice simplified formula. Okay? So that's about it. Let's have a look at it. Here we have our matrix, which had the negative eigenvalue, negative 7, 8, and so on. And the normalized power iteration failed. But now I'm going to apply the improved power iteration, the one with Rayleigh quotient, and that's actually default for my procedure. You can see that I do not really specify any method here. I just specify the initial vector, which is the same as before, because here I used 1, 0, so also down here I will use 1, 0 for comparison, and let's see what happens. And in about 11 iterations, we are getting estimate of the eigenvalue negative 3. That's what we expected. And the vector seems to be 1, 1/2, which is the same direction, and it fits. When you pass to the opposite matrix, the eigenvalues switch signs, but eigenvectors stay the same. Let's check. So the eigenvalue lambda now I think is negative 3, and the eigenvector could be 2, 1 again. And the difference between AV and lambda v is 0, they are the same. Perfect. So this is a really good iteration, and I would say it's sort of like a default method. It can handle all kinds of things. Let me show you. What you can see here is a matrix which is complex. In the second row, you can see 1 minus I and I. And I simply apply power iteration to this matrix. My initial vector is 1, negative 1. I don't care. And I get, well, that was a longer run, 31 iterations. But again, I don't care really very much at this moment. And over here, we can see that the eigenvalue is probably 1 plus I. Now let me put it into my code over here. Eigenvalue could be 1 plus I. But it's a little bit more difficult with eigenvector, because now when we are playing with complex numbers, we know not only multiply vectors by real numbers, but also by complex numbers, so they can rotate in the complex plane. And this vector actually has norm 1, the infinity norm 1. So it means that one of the entries has norm 1 as a complex number, has magnitude 1, but it's not very pleasant. And I do not quite see how to round it off. So what I often do, if I suspect that there should be a nice direction, I simply make one of the coordinates equal to 1 just by dividing the whole vector by that coordinate. So here I decided, I have a code here, to divide the first coordinate by itself, and so also the second coordinate by the first coordinate. And when you get lucky, you get a nice vector out of it. Let's see. The first coordinate is now essentially 1. So that worked. I mean, it must have worked. I arranged it like that. And the question is about the second coordinate. Is it now nicer? I actually read 1 minus 1i. 1 minus I. That looks nice. So let's check, and yes, here we go. This checks out. So the power method, the power iteration, works really well. And I can even show you some justification for that. But before we get there, it's not all conquering. And one reason or one indication that something is, let's say, not all that great can be seen already in this example. Notice, I wanted to show you that we can also obtain complex eigenvalues and complex eigenvectors. And I use this matrix for that, which includes some complex entries. Why didn't I use a real-valued matrix? Because it's much nicer, isn't it? I mean, it would be much easier for me. Well, here is the problem. When you have a matrix which has real values and a complex eigenvalue, and now imagine that this is the largest eigenvalue, because that's what we are interested in, then for the real-valued matrix, there also must be another eigenvalue, which is the complex conjugate of this one. And these two guys have exactly the same magnitude. And therefore, if you apply power iteration to them, it will not work because the assumption number 2 is not satisfied. And what happens is that the power iteration cannot decide and it starts cycling. So when you see a cycle for this power iteration, for the Rayleigh power iteration, there are no problems with forgotten minus anymore. This one really works, but when you see cycling, that's an indication that actually the power iteration cannot decide. And that's something that we have to solve, we have to work on it. So that's one weakness of the power iteration. But if you ignore this situation, then essentially it works really well and we have a theorem to prove it. Okay, here we go. So here we have a theorem. And to explain it, I think I will need some room. Okay, so we have some eigenvalues. Here is 0, and the largest one is lambda 1. So it could be, let's say, this guy. They can be complex. So for instance, this is the largest eigenvalue, lambda 1. And now there are some other eigenvalues. And because this guy is the largest, then these other eigenvalues must be in a circle whose radius is given by the magnitude of lambda 1. Okay? And this is, by the way, called the spectral radius, and now you see why it is called the spectral radius. First of all, the set of all eigenvalues is called spectrum of a matrix. And the spectrum is lying inside a circle whose radius is spectral radius. So that was easy. We denoted it rho. Anyway, now we look at the other eigenvalues. And according to the formula here, we have to look for the second largest, essentially, and check how large it is. So the second largest eigenvalue could be, for instance, this one, or this one. So this distance is m. We will need it soon. Let's go on. We pick some initial value, some initial vector, and generate lambda k xk using the Rayleigh power iteration, or just simply called power iteration. And then it says, and this is where it gets a little bit imprecise, it assumes, but it's hard to describe it somehow, so typically authors sort of skip this detail when they state this theorem, but we have to assume that this initial vector x0 actually does include the v1 components in it. And if it does, then the sequence xk converges to the eigenvector associated with the largest eigenvalue lambda 1, and the sequence lambda k, which we have over here, converges to lambda 1, which is wonderful. So the convergence is really now confirmed also for non-symmetric matrices, no problem about the basis at all. And moreover, there is some interesting information about the speed of convergence down here. What do we see? Let's have a look at the expression on the right. V1 minus xk, that's the absolute error of our approximation. It's the error of the approximation of the vector v for step k. And according to the specification there, the magnitude of this error should be big O of some expression. So we can imagine that it's proportional with some constant to this expression to power k. Let me just call it q to k. Now, what is q? Q is the ratio between the second largest and the largest eigenvalue. And we know that a geometric sequence converges quickly, really fast, if q is close to 0. Which means that we want the largest eigenvalue to be much larger than all the other eigenvalues. The separation, if it's large, then we can expect quick convergence for our power iteration. On the other hand, if we observe that the iteration is slow, that we need many, many iterations to actually get to some answer, then it suggests that our largest eigenvalue has a competitor which is not quite equal but close. Okay? So the separation is important. And of course, if there is a competitor which is exactly of the same magnitude, then it breaks down totally and you get a cycle. Okay, what does this mean about the error of the k plus first iteration? So it's c times q to k plus 1, and I can factor out 1q. Now it's just q to k. And this is q times the error of the kth generation. So this actually sends us a signal about the rate of convergence. We are comparing errors for the kth and k plus first iteration, and we can see that this iteration is of order 1. This is a method of order 1, which normally we take as a not so great. But finding eigenvalues, eigenvectors is a really tough work, so we are happy that we have a method of order 1. We are really happy with it. Okay? Under some circumstances, the convergence is even faster, but this is, let's say, a little bit more advanced theory, so let's not worry about it too much. Now, when it comes to the error of the lambda estimate, then we look at the formula, and we see that actually the power is 2k. What does it mean? Well, okay, little corner here. Q to 2k is simply q squared that all to k. So it's another geometric sequence where the basic number, the base of it, got squared compared to this geometric sequence. So there will just be q squared e lambda k. Again, it's a linear convergence, but this time the constant of convergence is squared, and remember, q is smaller than 1. So when you square it, it becomes even smaller. In other words, the lambdas in our iteration are expected to converge faster than the vectors. Okay? So that was the good news about the power iteration. So it's a nice method. It converges under many, many circumstances. Really, the only problem it has is more candidates for the eigenvalue. When you have also another problem, theoretically, an eigenvalue of higher multiplicity, this is really not such a problem in applications when you run the power iteration, because formally this assumption is not satisfied. You have several eigenvalues that are actually the same, so this chain is not true with sharp inequality. But when you run the iteration, it simply picks some eigen direction. When you have an eigenvalue of higher multiplicity, it means that it has an eigenspace which has higher dimensions. So there are eigenvectors going in different directions, and the power iteration typically chooses one and runs with it and provides you with the answer. So that's not fatal, okay? Eigenvalues of higher multiplicity, not such a big problem. This is a big problem. Another good question is, okay, you find the largest eigenvalue, and let's say that you are happy. If you just need to know the spectral radius, that's all you need. But sometimes you need also the other eigenvalues. How do you get them? So these are two good questions. What to do when you have a tie, and how to get other eigenvalues. And it turns out that we can actually handle both of them with the same trick, with the same idea. So let's make some room for it. One possible approach is to use rules for operations with matrices. We actually met one such rule before. I just casually mentioned that when you have a matrix and you pass to the opposite matrix, then the eigenvalues also switch signs. Now, this is not going to be real helpful, but it points the right way. Let's have a look at it. We have a matrix. And this matrix has some eigenvalue and the associated eigenvector. Now I'm going to perform a special operation on this matrix A. I'm going to subtract mu, which is a real number, or complex number even, times identity matrix of the same dimension. So this is actually a diagonal matrix where on the diagonal you've got the numbers mu. And when you subtract it, this essentially means that this new matrix is just like A, but all the diagonal terms have mu subtracted from them. If mu is positive, then we can imagine that on a real line, those diagonal terms are shifting to the left. So I'm going to call this a shifted matrix, although it's not exactly precise because I'm shifting just the diagonal, but shifted matrix. Okay, when I shift a matrix like that, then the eigenvalues also shift, and the eigenvectors stay the same. You can understand this as a message about one particular eigenvalue. I have an eigenvalue lambda, and then this shifted matrix must have eigenvalue lambda minus mu. Or you can see it as a message about a set of all eigenvalues. I can see them on a real line, perhaps, or in the complex plane. And if I shift a matrix, let's say to the left with positive mu, then all the eigenvalues as a family, they shift to the left as well. But the eigenvectors are preserved. That's very useful. How do I know that this is true? Good question. Well, let's see a proof. Okay, I will take this matrix and let it act on some eigenvector v. What will happen? Well, let's see. I can simply multiply out, this is no problem, AV minus mu ENV, and then AV, because V is an eigenvector, there must be some eigenvalue, let's call it lambda, which appears instead of multiplication by A. And over here, identity matrix times some matrix or some vector is still the same thing. So I just ignore this identity matrix. And finally, I am factoring out, and I get lambda minus mu multiplying the vector v. And now I look at it, and I go back to linear algebra, and I say, oh, wait a second. This is exactly the formula that I need to proclaim that this matrix has this eigenvalue with this eigenvector. So it all fits. That was easy, a nice proof. Okay. So we can trust it now, but how do we use it? Well, let's go back to our very first example. I have it over here. That was the 2x2 matrix. Here we go. And we ran the power iteration. Actually, do I have it somewhere here? Okay, let's run it. Let's run it again. So I'm going to run the power iteration with the initial vector 1, 3, just as before. And I can see here eigenvalue 3. And we check that it's true. So here's my picture. Matrix A. Here is a real line, and my eigenvalue is over here. That's 3. And this means, and we check that this is the largest one by trying different initial vectors, there is no eigenvalue to the right, and also there is no eigenvalue to the left of -3. So somewhere here in this range, there is a second eigenvalue, or perhaps even more, if the matrix were larger. So there might be some eigenvalue somewhere here hiding. I don't know. And what happens when I shift my matrix, let's say to the left? Well, the eigenvalues, they all shift to the left. If they shift by a little bit, then I don't see any change, any major change. But if I take all these eigenvalues and shift them quite a lot, then this eigenvalue 3 is no longer the largest one. Another guy gets promoted, and I can find this other guy using power iteration. And that's the whole idea. By shifting the matrix, I will change the relationship in the spectrum, in the set of all eigenvalues, and use it. Okay, how do I make sure that shifting puts the formerly dominant eigenvalue 3 out of the game? Well, I don't know the other eigenvalues, so I cannot do some balancing act, but I can instead do some reasoning. If I shift 3 all the way to 0, then if there is some other eigenvalue, it will definitely get promoted. Yeah, let's try it. So I'm going to shift by 3 in this case. So I'm actually using mu is equal to 3. And this is the A minus 3E E2. I'm using E2, matrix 2 by 2, so that the dimensions fit. And all the eigenvalues, they nicely shift to the left. And one of them definitely becomes the largest one. So let's have a look at it. For mu, I am taking 3. And I define a new matrix B. Now, by the way, just out of curiosity, when I shift eigenvalue 3 to 0, it means that this shifted matrix, which I'm calling B over here, has 0 as eigenvalue. What does it mean? It means it's singular. A singular matrix, which is 2 by 2, must have one row to be a multiple of the other. Does it work? Let's have a look at this B. Oh yeah, one row is the multiple of the other, so it all fits nicely together. Warm feeling. We like mathematics for that, of course. It makes sense. Everything makes sense there. And now we apply power iteration to this matrix B, to the shifted matrix. But otherwise, I'm not making any changes. I just use the same vector. Everything is the same. And I run it. And, oh, it was a fairly short run. I got eigenvalue -4. So there is some eigenvalue. Okay, if this is 3, then somewhere... Okay, this is a little bit unfortunate. Somewhere here is -4. That's my new largest eigenvalue of the shifted matrix. But I don't care about the shifted matrix. I care about A. What do? I just shift back. So I'm shifting back. And if I start at -4, I'm shifting by 3. I end up at -1. Is that true? Is -1 eigenvalue of my matrix? That's a good question. Let's try. I have this code here. So I'm putting -1 into the code for lambda, and the eigenvector looks like 1, 1. Yeah, okay, there's not much to think about. Let's check, and we got vector 0, 0. We are right. This is all correct. We just know all eigenvalues of the matrix A, because it's small. If this matrix were larger, then there would be some other eigenvalues, most likely, and they would have to be between 3 and -1. So what we just did, we found the range for all the eigenvalues, if they are real. If they are complex, that's another story. Okay? Does this work always? And the answer is essentially yes, for real eigenvalues. Imagine that the largest eigenvalue is negative. So it goes like that. Here is 0, here is the largest eigenvalue, and there are some other eigenvalues floating around that are smaller in absolute value. This time I'm going to shift to the right so that the largest eigenvalue becomes 0 again. All the eigenvalues, they shift also to the right, and power iteration finds this one. I shift back, and again, I have the range for all eigenvalues. So this is a very useful procedure. It provides us with 2 eigenvalues and with information about the location of all the others, if there are any. Moreover, it can do a good job for us if it happens that our iteration doesn't work. Why doesn't it work? Because there are 2 candidates for the largest eigenvalue. One here, one here. I start power iteration with some initial vector. I see a loop, and I say, okay, wait a second. There is a tie for the largest eigenvalue. So what I'm going to do, I'm going to shift in one direction. I don't care which one. The important thing is I'm changing the balance. When I shift just by a little bit, then one of these 2 guys gets promoted to the top job, and power iteration finds it. So this shift of a matrix actually solved the last remaining problem of power iteration. What to do when there are more candidates for the largest eigenvalue. So right now, we should be able to find the largest eigenvalue for any matrix, which is wonderful. This shift is quite useful, so I actually taught my procedure to do it for me. I don't have to bother shifting the matrix manually. I can simply start with the original A, and I ask, pretty please, for this matrix to be shifted by 3, which is exactly what we did in our example. And let me run the code. Let's see. First, the procedure is informing me that it's working with a shifted matrix. And because it's working with a shifted matrix, the same that I did manually before, we should get the same iterations. And we did. Those 3 lines of code, they are exactly the same. And then at the end, when the procedure reached the stopping condition, it took lambda -4 and shifted it back for me to -1, so I can just read the answer. Very convenient. Let's try it. Here is another 2 by 2 matrix. And let me run power iteration with this matrix, initial vector 1, 1. Why not? Here we go. What do I see? Well, I see actually it's a cycle. Iteration got into an infinite loop. And when I look at it, I can see that every fourth vector is the same. 1, 2, 3, 4. Yeah, every fourth vector is the same. So this is a loop or cycle of length 4, which suggests that there are two eigenvalues competing, two distinct eigenvalues competing for the top job. So I'm going to shift the matrix, let's say by 1, which means to the left by default. We are subtracting by default. I shift it, let's say by 1 to the left. That should solve the problem. So I'm calling my procedure with A, and I'm asking for shift by 1. Here we go. That was quick. Okay. Again, we stopped prematurely with a warning, and I look at the vectors, and I can see that here we have another loop or cycle. This time the length is 2, which is perhaps better, but still not good. How is that possible? How it's possible that I shifted my eigenvalues to the left and the tie did not get broken? Well, let me show another picture. This is the picture for real eigenvalues. When they are complex and my matrix is real, which is this case, then the complex eigenvalues come in pairs. We talked about it earlier. So here it is. I have two complex conjugate eigenvalues which have the same magnitude, and therefore they compete for the job of the largest eigenvalue. What happens if I shift by 1 to the left? Well, I get new eigenvalues, let's say here and here, and they happen to have the same magnitude again, and they are distinct. So of course I do get a loop. What else can I expect? Well, how do I solve the problem? I have to shift in a different direction. By the way, this is the real part, or the real axis, and this is the imaginary part, okay? That's the complex plane. I didn't explain. I hope it was clear from the context. So I'm going to shift in the direction of the imaginary axis, which means I have to use complex imaginary shift of the matrix and also of the eigenvalues. And that should solve the problem for me. Now, if I shift by I, again, it means I'm subtracting I, I'm shifting downwards. So I shift by I can picture these eigenvalues going down, and one of them becomes dominant. I bet my shoes on it. Here we go. So, going back up, shifting by I, and that was a fairly short run. And at the end, what do I see? I see a number which looks like eigenvalue 1 minus 1i. 1 minus I. That's a complex eigenvalue. Let me put it here. 1 minus I. How about the vector? Well, that's a little problem here. We know that we can take any eigenvector multiplied by a non-zero number, we get another eigenvector. So the procedure is choosing from all these multiples. Once we start playing with complex numbers, we can also use complex multiplication when we are playing with vectors. So you can take a really nice vector, let's say 1, 1, you multiply it by a complex number, and it becomes, I'm not saying ugly, but it becomes, let's say, less convenient. So I think, okay, is there another vector which is just a complex multiple of this one that looks more friendly? And you never know, but you can try something. For instance, I can try to divide by the second coordinate. It becomes 1 then, which is nice, and we will see what happens with the first one. Actually, this is a school problem, you know, so I'm really hopeful. After multiplication or division by the second coordinate is 1, essentially. There is some complex unit, but it's multiplied by 10 to negative 17, so it's gone, essentially. And the first coordinate became 2 minus 1i. Yeah, it is nice. So I strongly suspect that the eigenvector is 2 minus I and 1. Let me check. Bang. Yeah, it is. Wonderful. It does work. That's wonderful. By the way, I can also start with a complex initial vector, and I will get the same information, but perhaps a different eigenvector, because it will be a different multiple. Okay, I do it over here. Here the initial vector actually has some i's in it. And it's a good idea to start with complex initial vector if you suspect that your eigenvalues are complex, because you need to get this complex thing into your procedure. If you start with a real matrix, a real initial vector, then you can never get to complex eigenvalues. Let me just run it out of curiosity. Yeah, it works. I got vector 1 minus I, and again the eigenvector is not really friendly, but it's a different unfriendly vector. as expected. And I strongly suspect if I divide by the second coordinate, I will get the nice guy that I had before. Anyway, we discovered that there is eigenvalue 1 minus I, which is actually somewhere here, just 45 degrees. So there will be another one on the top, 1 plus I. Common sense tells us. How do you find it? Well, we shift in the opposite direction. I'm shifting by minus I, which means I'm adding I. I'm shifting everything up. And this time, the procedure gave me 1 plus I with another funny vector. Okay, I will try dividing by the second coordinate. And is it nicer? The answer is yes, it's 2 plus I. So the second eigenvalue is hopefully 1 plus I, and the eigenvector is 2 plus I, 1. Does it work? Yes. Wonderful. That's great. So we can break a tie. We can find the range for our eigenvalues. But what if a matrix has more eigenvalues? They are hiding in the middle. How do we get at them? That's a good question. Let's have a look at an example. I have a 3 by 3 matrix over here. A nice one. Okay, here we go. I'm going to run power iteration with initial vector 1, 1, 1. Why not? And we get a cycle again, length 2. By the way, if you see cycle length 2, then typically this is not a case of complex eigenvalues, but two real guys competing. If the cycle is longer than 2, then you are sure that there are some complex numbers behind it, by the way. If you are curious, how do I know? Check out the lecture notes. Okay, so we know what to do. I have a tie for the largest eigenvalue, so I'm going to shift. And I think, I'm hopeful, that this is actually just a real valued problem. So I'm shifting by 1. And we will see what happens. Well, I'm getting a candidate called -4. So let's make a little picture. Here is 0. Here is -4. And the eigenvector seems to be 1, -1/2, 1/2. If I multiply by 2, it becomes a bit friendlier. I don't have to write fractions. That's the main advantage. So 2, -1, 1. That should be the eigenvector. Let's have a look at it. I have the checking code prepared here. -4 and a 2, -1, 1. Does it check out? Yes, it does. Okay, so let's shift in the other direction. And I would be really surprised if it didn't confirm +4 as an eigenvalue. Now, that would be a shocker. Fortunately not. Okay, here is another guy, 4. With eigenvector. Okay, again, I'm going to multiply by 2, and it becomes 2, 1, 1, essentially. School examples are cute. Okay, here we go. Lambda is equal to 4, vector 2, 1, 1. Does it check out? Yes. Great. Are these really the largest eigenvalues? Perhaps I started with the initial vector that does not see an eigenvalue which is even larger. I don't know. We will see. I don't have to worry about it now, because if I find a third eigenvalue, I will know that it's somewhere here or perhaps there. I will see where it is. Anyway, the probability that I missed out on a larger eigenvalue is very, very small. So I suspect that there is an eigenvalue somewhere in the middle. How do I get it? Well, obviously, by shifting the spectrum, by shifting the eigenvalues, this guy in the middle can never become the largest. So we need a new trick. We need a trick which takes this situation, this picture, and turns it around, inside out, so to speak. Something which changes small numbers into large and large numbers into small. Do we know such an operation? The answer is, well, many. But probably the simplest operation is when you take 1 over x. 1 over x, that's a function which changes small numbers into large ones and large ones into small ones. So let's have a look. We have a matrix with eigenvalue and eigenvector. And now we look at the inverse matrix. And I claim that the original eigenvalues get reciprocated, if there is such a word. And if not, okay, I just invented it. And the eigenvectors again stay the same, which is very convenient. How do I know that it's true? I prove it. Now this time the proof is also simple, but different. If you start by applying A inverse to V, you are not going to get too far. So instead, I will start with this information. Lambda is eigenvalue, V is eigenvector. So AV is lambda V. Now, assuming that lambda is not 0, which typically it's not in applications, and if it is, we recognize it and we actually have the information, I can divide by lambda, and it comes here. How about A, where I cannot divide by A because it's a matrix, but I can multiply by A inverse, and I have to be careful. I multiply by A inverse from the left. Here it cancels, and here it appears. And now I look at it and I say, oh, that's exactly the equation I have been looking for. Matrix A inverse has eigenvalue 1 over lambda with eigenvector V. And it's done. Very nice. Okay, let's have a look at our example. I have a matrix A, I know 2 eigenvalues, so I'm going to ask Maple to prepare the inverse matrix, I call it B, and I'm going to apply power iteration to this matrix B, again with the same initial vector, why not? And we will see what happens. Bang. Well, I look at it and I see 1/2. So the inverted matrix has eigenvalue 1/2. How do I get back? By inverting again. So my matrix should have eigenvalue 2. Let me put it somewhere here. Do I see a code somewhere here? Over here. Eigenvalue 2. How about the eigenvector? Eigenvector, okay, that wasn't smart. I should have copied the code over here. Eigenvector is 1, 1/2, 1. So my suspicion is 2 with eigenvector 2, 1, 2. Okay, let me check. 2, 1, 2. Do I remember it? I think so. So 2, 1, 2. Let's run it. Okay, it looks as if I didn't do anything. So I move it down and I run it again. Okay, we got 3 zeros, 0 vector. So we confirmed the third eigenvalue. Wonderful, it does work. That's a very good trick. Okay, we found 3 eigenvalues for our matrix A, and we are happy. We know the spectrum, we know all the eigenvalues, eigenvectors. What if we had 4x4 matrix? Then we need 4th eigenvalue, which is hiding somewhere. By the way, what type of eigenvalue do we find when we use the inverse? All the relationships change. When you find the largest eigenvalue of A inverse, you are in fact finding the smallest eigenvalue of the original A. So 2 is the smallest eigenvalue, which means there is no other eigenvalue between 2 and -2. So if there were some other eigenvalues hiding, they would have to be between 2 and 4, or between -2 and -4, in these 2 regions. How do we find them? Well, shifting doesn't help, and inverse does not help either, because if some eigenvalue is here between 2 and 4, after the inverse, it will be between 1/2 and 1/4 again. We have no chance of finding it. So, there is an interesting idea. We are going to combine these 2 processes, the shift and the inverse. And I claim that the matrix A minus mu En inverse has eigenvalue 1 over lambda minus mu and still the same eigenvector V. And the proof is very simple, just a modification of, actually you connect these 2 ideas essentially. You go this way, but you use instead of A, the shifted matrix. And it goes beautifully. Okay. What does it mean in applications when I use it? What happens? Well, I apply power iteration to this matrix, shift it and with inverse, and I get some, let's say, lambda tilde. Now this eigenvalue had to come from some original eigenvalue lambda, necessarily. And that's an equation that we can easily solve. Lambda minus mu is 1 over lambda tilde. lambda is mu plus 1 over lambda tilde. Now, what kind of eigenvalue did I find by this procedure? And how do I choose mu? Okay, let's think about it. This lambda tilde is the largest of all possible eigenvalues. In other words, if I go through all eigenvalues of A, not of this inverse matrix, but the A, if I go through all possible eigenvalues of A, then this ratio is as large as possible. This means that when I go to 1 over trick, this expression is the smallest possible. And this means that this lambda, if this expression is as small as possible, this lambda is the closest eigenvalue to mu. And that's how you pick mu. You use mu to fish for eigenvalues. You suspect there is an eigenvalue somewhere, so you set up mu, and you find the closest eigenvalue. Let's have a look at it. We actually know all the eigenvalues of this 3 by 3 matrix, and that's exactly what we can do to do some fishing, because we will expect some answers, and we will see whether we get them or not. So, I'm going to move to a code. My procedure can also do this trick, by the way. I taught it. Okay, that was the run. Here we played with it. Here we go. So I start with matrix A, and I ask for matrix to be shifted and inverted. So I just say inverse, and I specify mu. So if I do it with 0, I'm essentially asking for A inverse. So I'm asking for the closest eigenvalue to 0. Yeah, that makes sense. That's the smallest eigenvalue. And I run it, and I get 2, and the vector 2, 1, 2, essentially. Okay, so it works. What happens if I ask for the eigenvalue, which is closest to, let's say, 10? Well, based on the picture, this procedure should find 4. Let's see. It did. It found 4, and eigenvector 2, 1, 1, essentially. Yeah, it all fits. What happens if I ask for the eigenvalue closest to, let's say, negative 2. Okay, negative 2 is over here, and the closest eigenvalue is negative 4. Okay, we will see. Bang, and here we go, negative 4, exactly. What happens if we ask for the eigenvalue closest to 3? Well, what's the eigenvalue closest to 3? It's these two guys. There is a tie, so the iteration shouldn't be able to decide and goes into a loop. Let's see. Yes, we got a loop. There is a warning that we stopped prematurely after 50 iterations, and when we look at the run at the vectors, we can see that there are flip-flopping between two directions. All the estimates for lambda, they're also changing between two values. So it does behave exactly the way we expect it to behave. Now, here is an interesting question. I've been using initial vector 1, 1, 1 throughout the game. What happens if I use for my initial vector, which is 4, 0, 3? Now, I don't expect you to say anything now or to see the answer, because I didn't tell you what's so special about this vector. Let me tell you what's so special about this vector. When I was writing it, one of my eyes was sort of looking up. This is exactly the sum of this eigenvector and this eigenvector. It's a combination of these two guys, and because it's a combination of these two guys, when I do decomposition into a basis, into this basis, then this component does not appear at all, and therefore it cannot appear also in the iteration. In other words, this iteration, if I use it with this initial vector, does not see the eigenvalue 4 at all, because it does not see its eigendirection. And therefore, if I start now my iteration with this vector, the iteration will just see 2, it will see negative 4, and remember, I've been asking for the closest eigenvalue to 3. And if the iteration doesn't see 4, then it simply shows 2. If everything works the way we think that it works. So, 403, let me see. 403. I am not changing the center mu. I am not changing anything. I'm changing the initial vector. 403. Bang. We got 2. Yeah, it seems that we do know what's happening. Let me go back to the initial vector 111 so that we can see all the eigendirections. And let's try another interesting thing. What happens if I supply 4 as mu? So I'm asking for the closest eigenvalue to 4. And the procedure complains. It says the shifted matrix A minus mu En is now singular. And therefore we cannot find the inverse, and therefore we cannot run the procedure, which is not nice, but it actually is nice because we have the eigenvalue. This tells us that 4 is an eigenvalue. We have it almost for free. We just don't have the vector, eigenvector. So we ask for the closest eigenvalue to, let's say, 4.1, and we get the eigenvector. So this is no problem either. This is a very nice procedure. Just out of curiosity, how come that this run is really short? Previously we had like 13 iteration, 20 iteration, suddenly 5. Well, there is an interesting thing happening. I'm asking for the eigenvalue closest to 4.1. When I shift the matrix A by 4.1, then this essentially becomes, or effectively becomes 0. This eigenvalue is then almost 0, and the other guys are far from 0. Then we pass to the inverse matrix over here. And since these guys are sort of like apart from 0, they just become moderately large numbers. But this guy is almost 0, and therefore it turns into a really, really huge number. It will be negative in this case, but huge in absolute value. And therefore it will dominate all the other guys. And we had a theorem which said that the speed of convergence depends on the level of dominancy of the dominant eigenvalue. The more it dominates, the faster the convergence. So if you can choose your mu so that it's close to the eigenvalue that you are looking for, you will be rewarded by a really quick convergence. Just an interesting observation. Anyway, this procedure is nice. Let's give it a name. It's called inverse power iteration. Here is the slide. And there should be no surprises there, hopefully. We choose some mu. We create auxiliary matrix B, we run power iteration, we get the answer, some lambda, and then we use this formula. Does it fit? Yeah, the formula fits, so no surprise there. Very nice procedure. Let's give it another spin, and we will need more room because we are going to graduate from 2 by 2, 3 by 3 matrices to 5 by 5 matrices. Okay, so we are really tough. We are going to handle it. Okay, here we go. Here is my new toy. A 5 by 5 matrix, which is symmetric, by the way, which means that the eigenvectors should form an orthogonal basis. This will come handy later on. But you remember that was one of the assumptions in our initial investigation. Okay, let's run power iteration. I chose the initial vector fairly randomly, just some numbers that came into my mind, but probably are not too surprised when you see them. Here we go. After 24 iterations, we can see some candidates. I can see negative 60. That could be the eigenvalue. Here we go. And for the eigenvector, okay, this is a larger matrix, so things are becoming more difficult, and it takes more time for the iteration to settle down. And we had this theorem which said that LKs, the estimates for lambda, should converge typically faster than the vectors, and you can see it here. For lambdas, we already have really nice 60s, and they have been 60 for about 8 iterations, whatever. But the vectors, they didn't settle down yet completely, yet. We can see it here on the right. So I would guess that if a number is very small, if it's 10 to negative 6, then it's most likely attempt at 0, because this is a school problem. We're expecting nice answers. So I think that this vector is 0, negative 1, 0, negative 1, 0. And I just flipped the sign because I'm too lazy to type all these negative signs. Here we go. Let's check, and it checks out. So we have our first eigenvalue and eigenvector. And we will need more room for those eigenvectors now. Okay. 0, let's say here. Okay, this is supposed to be the largest, so it's negative 60. Let me put 0 somewhere here. and here negative 60. The eigenvector is 0, 1, 0, 1, 0. Is this really the largest eigenvalue? Well, most likely yes, because the vector which I chose, well, I would have to be really unlucky to miss on some direction. But just to be on the safe side, let me try to change 3 into 4, and we are still getting negative 60. You may think that changing from 3 to 4 is not really a substantial change for a vector. That's true. But it's a very big change for the vector decomposition. When you are decomposing with respect to some basis, this has a big impact. So this is a big change. How about changing 13 to 14 over here? Another big change, and we are getting negative 60. How about if I change the sign to plus 13? Yeah, we are still getting a negative 60. I could play like that for a while, but yeah, this is the largest eigenvalue. So, what's the next step? The next step is to neutralize it by shift. We change it into 0, so we are going to shift to the right, so mu have to be negative 60. It has to be a negative number. Okay, here we go. Matrix should be shifted by a negative 60. Here we go. Okay, 36. What did I just find? I found the rightmost eigenvalue, 36. Hopefully. Again, I should try different initial vectors, but it is. Okay, if this is 60, then 36 is somewhere around here. Well. I think that 0.00001 is about 0, attempt at 0. The same with in the fourth coordinate. So this looks like 10101 to me. 10101. My new check goes like this. 36, not 360, 36. And this vector will be changed into 1011010. Yeah, it checks out. By the way, you may notice that these two guys, these two vectors, they're perpendicular. If you form the inner product, they nicely cancel each other out of zeros. Beautiful. Okay, what next? Now we should pass, it seems like a good idea, to the inverse matrix to find the smallest eigenvalue, the eigenvalue closest to 0. Okay, here we go. I'm going to change my matrix specification into inverse. Somebody stole my, oh, here it is, cursor. Couldn't find it. Inverse, and center will be 0. Bang. Okay, so the procedure is complaining. I ran out of allowed iterations. When I look at the vectors, I can see a cycle of length 2. So there are two guys competing for the title of the closest eigenvalue to 0. So I'm going to shift my point of view subtly. I'm not going to ask for the closest eigenvalue to 0, because there are two candidates, most likely, but the closest eigenvalue to, let's say, 3. Why not? 3 is a nice number. Okay, here we go. That's a long run. Inverse with center 3. And I'm getting 12. Here we go. Which is 1/3 of 36. It's over here, 12. How about the eigenvector? Okay, this time it looks interesting. I strongly suspect that this is supposed to be negative 1/2, 3/4, 1, negative 3/4, negative 1/2. Okay, so what happens if I multiply it by negative 4? The answer is it becomes much nicer. So, okay, let me write it down. I'm multiplying by negative 4, and I'm getting 2, negative 3, negative 4, 3, 2. That's a nice vector. Okay. And we need to check that 12 is eigenvalue, and 2, negative 3, negative 4, 3, 2 is an eigenvector. You probably didn't expect such a nice eigenvector with different numbers than 0 and 1. Okay, it checks out. So we've got another eigenvalue, and because we know what's happening, we think that negative 12 will be another eigenvalue. So let's hunt for it. Let's ask for the eigenvalue closest to, let's say, negative 11. Why not? Yeah, we got a really short run, exactly as expected. Negative 12, eigenvalue. And the eigenvector could be, okay, this time it looks okay. I don't have to really do anything. 1, 1, negative 1, negative 1, 0. Okay. Negative 12, 1, 1, negative 1, negative 1, 0. Let's check. Yeah, it works. So, we've got 4 eigenvalues. We need to hunt for the 5th one. Where could it be? When I ask for the closest eigenvalue to 0, I got a tie. Let's just make sure that there's nothing hiding here. I will ask for closest eigenvalue to 0.1, and I should get 12. And it should be a really long run, because when you ask for the eigenvalue closest to 0.1, then 12 and negative 12 are really close. So perhaps, yeah, that wasn't really nice, because the balance was too even, and therefore the iteration needs many, many, many iterations to reach the answer. So let's ask for the eigenvalue closest to 0.5, let's say. This is nicer. And the answer is 12, essentially. I can see lambdas moving to 12. So we can be pretty sure, if I ask the eigenvalue closest to 1, we should get 12 now. Yeah, we are getting 12. Good. We can be pretty sure that there is no eigenvalue between negative 12 and 12. Or perhaps there is one, but our initial vector doesn't see it. So just out of curiosity, let's try again a slightly different initial vector, 4. Okay, still 12, the closest one. So the eigenvector, the initial vector is not at fault here. There really doesn't seem to be any eigenvalue. So let's hunt. Another possible location is here. I've been asking for the largest. I've been asking for the closest to 0. I didn't ask about this. So what is the middle? Okay, the middle is 12, 36, 24. I am going to ask for the eigenvalue closest to 24. Here we go. And I got an infinite loop, length 2. What are the options? First, the possibility is that there is an eigenvalue, and I do not see it because my initial vector does not include this direction. So I should try different initial vectors, and I still get this infinite loop. So that's not the cause. Another possibility is that there are 2 eigenvalues equally close somewhere inside. But it's impossible, because that would mean 1, 2, 3, 4, 5, 6 eigenvalues. Not possible. So this leaves me with the only one conclusion. There is no eigenvalue inside, and this loop that we can see, this infinite cycle, is caused by 12 and 36 fighting for the position. Just to make sure that this is really the correct conclusion, let me ask for the eigenvalue closest to 26, let's say. And we should get 36, and we are getting 36. So there is nothing over here. Okay, how about this range? Well, what's the middle? The middle here, well, we just take the average. So we add and divide by 2, and we get negative 36, which is a nice coincidence, but it's a coincidence. Okay. Let's ask for the eigenvalue closest to negative 36. That's not minus, that's minus. And we are getting another loop. Again, we can see that the vectors are not approaching somewhere, but they are oscillating. There are 2 vectors flip-flopping. We can see it nicely in the 2nd coordinate or in the 4th coordinate. So again, it seems that there are 2 eigenvalues fighting for position, and it cannot be 2 new eigenvalues, so it must be these 2 guys. Just on the safe side, to be on the safe side, let me ask about the eigenvalue closest to, let's say, 38. And we get negative 60. And let me change the initial vector, again, just to be on the safe side. Let me put 13 here. and we are still getting negative 60. So the initial vector is not to blame. It really does include all the possible directions, it seems. The problem is that the fifth eigenvalue is nowhere to be found in these gaps. So where is it? Well, it will have to be one of these four. One of these four eigenvalues has higher multiplicity. And here we can see the first disadvantage of this approach, of the inverse power iteration. It does not help us with eigenvalues of higher multiplicity, unfortunately. Does it have some other disadvantages? And the answer is yes. The second important disadvantage is that you want to have some procedure which can be put into a computer so that the computer finds the eigenvalues for you. But you can see that you have to use quite a lot of reasoning when choosing mu, when analyzing the output, reasoning out what's really happening. This is difficult to put into a computer. I mean, it's really difficult to teach a computer how to think. Nobody really succeeded yet. So this algorithm is not the best for computers. The third reason why this algorithm is, let's say, not so popular is that finding inverse matrix is very expensive. We talked about it, n-cubed operations roughly. This is bad. If the matrix A is a million by million, you definitely do not want to take an inverse matrix of something. So there are some good reasons to look for an alternative. But still, remember, this shift is cheap because you don't have to do inverse matrix. And it is very useful when two eigenvalues are competing for the same job. And then there is essentially no substitute. You do have to use shift. This is the most efficient way to handle the situation. So I'm not knocking down the whole approach. We should definitely take away this shift operation, at least that one. And this one can help as well. I actually enjoy fishing for eigenvalues. This is like a detective work. I enjoy it, but yeah, there are some disadvantages. Okay, let's erase it. And let's look at a new approach that could also help us in finding other eigenvalues. It's not going to help us with the tie. Okay? For the tie, we have the shift. But other than that, let's try some completely new idea, which actually will be an old idea. You will see. No spoilers. Here we are. We have a matrix, a beautiful 5 by 5 matrix, and we found the largest eigenvalue using power iteration. To get other eigenvalues, we need to remove it from consideration, get it out of the picture, which we did by shifting. We shifted it to 0, it became irrelevant. However, the shift trick only yields another eigenvalue, and that's it. It cannot yield more. So we need another trick, how to neutralize this eigenvalue. And this is the moment when we take inspiration from the world of operating systems. If you remember, we had this complication that the initial vector perhaps does not include this direction or that direction, and it could hide some eigenvalues from us. Well, we are going to say, well, it's not a bug, it's a feature. Yes, we can actually make some directions disappear by smartly choosing initial vector. So, I have my eigenvalue, I have my eigenvector, and if I choose my initial vector so that it does not feature this direction, then the iterating procedure, the power iteration, will not see this eigenspace anymore. It will not see this eigenvalue anymore. And if I run power iteration, it should find the second largest eigenvalue. That sounds like a neat idea, which can be recycled. We can remove more directions by smartly choosing the initial vector. Okay, how do we do it in practice? We have a nice vector here, we found it, our first eigenvector. How do I find initial vector which does not feature these components? I actually did a trick like that before. I used initial vector which combined the other directions. But the problem is, normally I don't know them. I just know this direction. How do I find a vector which does not use it as a component? Well, let's have a look at a simple picture. Here is my vector v1. The first eigenvector. And I'm wondering, okay, how should I choose my x0? And you may think, why don't you take a vector which is perpendicular? Okay, here is my vector which is perpendicular. This could be x0. Does it use the component v1 or not? And the answer is, I don't know. Nobody knows, because it all depends on v2. Let's imagine that v2 looks like this. This is v2. What is the decomposition now? we have to use parallelogram, whatever they call it, like that, like that. And this is the decomposition of vector x0 into our basis. And we can see that this vector is actually a sum of these two components, and we are using component v1. We didn't avoid it. So unless we know all the other vectors in the basis, we are unable to create x0 which does not use direction v1. So this looks like a dead end. It's not a dead end, but it's something which forces us to restrict our attention to matrices that are, in a way, nice. So I'm going to look at matrices now A, which have this property that when you look at the eigenvectors, they not only form a basis, but they form orthogonal basis. What does it mean? It means that all the vectors are mutually perpendicular. And in such a world, in a space with such a basis, orthogonal basis, this trick with perpendicular x0 will work. And therefore, in such a world, we can do the following trick. We use power iteration to find the largest eigenvalue. Lambda 1, v1. Then we choose some initial vector x0, which is perpendicular to v1. We run power iteration, and we get the second largest eigenvalue. Or perhaps not. If there is a tie, then we shift the matrix. We know how to do these things. We don't have to worry. Then we find an initial vector which is perpendicular to v1 and also to v2. Let me put it like that. I should put x0 perpendicular to the span of these two vectors. Okay, it's okay. And we get the third largest eigenvalue. Or perhaps there is a tie and so on. Let's ignore the details now. Then we find x0, which is perpendicular to v1, v2, v3, and these are all vectors. And we get lambda 4 and v4. And we keep going until we find lambda n, vn. All the eigenvalues. Theoretically, perhaps, we will see. Does it look good? Yes, it does look good. Now, what are the chances of actually having orthogonal basis when you get a matrix? And the answer is, well, there is this theorem, this fact that I recalled from linear algebra. If your matrix A is real and symmetric, then you do have a basis of eigenvectors, orthogonal basis of eigenvectors. So this is really something that does happen in many examples. And our 5 by 5 matrix, let me go back to it. Let me see, over here. Our 5 by 5 matrix is real and symmetric. So eigenvectors do form an orthogonal basis. And you can actually check that these 4 guys over here are mutually perpendicular. There is a 5th guy missing. We will see. How does it work now? We start power iteration, and I can use the same vector that I used before, and I'm not doing any shifts or inverses. This is exactly what we did before. We run power iteration with some x0, and we get the largest eigenvalue. So the initial vector, okay, somewhere here. It's some vector, I'm not going to write it. The important thing is power iteration provided us with lambda 1, which is negative 60, and vector v1, which is 0, 1, 0, 1, 0. Okay, I'm going to use row notation to save some room. What next? Well, we need to find initial vector x0, which is perpendicular to this v1. Now, perpendicular means I have 0, 1, 0, 1, 0, and I'm looking for a vector which works like that. When I multiply the corresponding coordinates and then sum up, I should get 0. Well, the easiest way to do that is to put 0 here, and now it's guaranteed that these two guys will be perpendicular no matter what I put over here. So just to make my life easier, I put 0 here, and okay, I want something there. I cannot take 0 vector, so I put, let's say, 1 here, 1 here. Is it a nice vector? I hope so. So my next initial vector will be 1, 0, 1, 0, and 0, and I apply power iteration to this initial vector and matrix A, no change to the matrix. And when I do that, Okay, I feel sorry that I have to remove those 13s actually, but okay, that's life. I could use vector 13, 0, 13, 0. Okay, let's leave it like that. And we are getting 36 for the eigenvalue, and the eigenvector seems to be really 1, 0, 1, 0, 1. So far, so good. So now we have two eigenvalues, two eigenvectors. Lambda 2 is 36. V2 is 1, 0, 1, 0, 1. And we are looking for eigenvector that would be perpendicular to these two guys. Okay? Let's see. 0, 1, 0, 1, 0. 1, 0, 1, 0, 1. I'm looking for a vector which is perpendicular to this one and also to this one. So I'll handle this guy first. I put 0 at the second and fourth coordinate, and now these two guys are perpendicular. How about these two guys? For instance, I can put 0 here, 1 here, negative 1 here. Okay, so our next initial vector is 0, 0, 1, 0, negative 1. And we use it to start our power iteration. And actually, with negative 60 and 36 out of the picture, I expect to see an infinite loop. Definitely. Let's have a look at it. I'm changing the initial vector to 0, 0, 1, 0, negative 1. And I'm getting infinite loop. Okay. What do we do with this? The answer is, well, this tells me that there is a tie for the next largest eigenvalue, so we shift the matrix. Okay, let's shift the matrix. So we are actually using the operations after all. Matrix is shifted, let's say by negative 1. I'm going to shift it to the right. And I'm getting negative 60. How come? How is it possible that my power iteration actually provided me with eigenvalue and eigenvector which is perpendicular to the initial vector? Because we can see the eigenvector here. It's essentially 0, 1, or 0, negative 1, 0, negative 1, 0. That's perpendicular to this one. How is that possible? And the answer is, this idea is very nice. This whole idea about perpendicularity, things like that. But it only works theoretically, or it works if we do the calculations precisely. For instance, if I forced my system to work just with integers and rational numbers, then these calculations would actually work. But my system is working in the floating point form, and therefore there are some rounding errors. And because we have rounding errors, then these vectors xk are not exactly what they're supposed to be, but they're slightly different. And because they're slightly different, this forbidden direction actually found its way into my vector. And it was there, and it was very, very tiny. And this iteration stopped very early. It was like 12 iterations, if I remember. So this was a very short run. And even though this dominant direction found its way into this one, I'm sure about it, it didn't have time to assert itself, to appear in the output. But here the run was longer, it seems. And therefore, our forbidden direction, the dominant direction, had a time to reassert itself, to show its dominance, and it won. So that's actually a serious concern. That's a big problem for all these methods, and especially for methods which actually use this trick with perpendicularity with forbidden directions. This is a big problem. We need to somehow solve it. And we actually have more motivations for that. Let's imagine that by some miracle, this would actually work, or perhaps with a better system. I can imagine that if I ask for double precision or triple precision, then perhaps we would get another eigenvalue, most likely 12 after a shift. We do it a few times, and then we have like 4 vectors. And we need to find a vector which is perpendicular to these 4 guys. How do I do it? Well, it's no longer going to work like that I just look at them and dream it up in some intuitive way. So this is a very serious concern. This procedure is very nice while you are here looking for perpendicularity to 2 vectors, 1 vector, this is okay. 3 vectors, this is already an adrenaline sport. 4 vectors, 5 vectors, this is really bad. You could use some trick from linear algebra. Essentially, you would choose a vector by random, and then you would use the Gram-Schmidt orthogonalization process, whatever it's called. But actually, when you think about it, there is the same problem in the iteration and also at the start. In each case, we have a problem that there are some directions which are not wanted, and we want to get them out of the game. So we can actually use the same trick throughout the iteration, even at the very start. We have the initial vector x0, and perhaps we choose it randomly, and we need to remove the unwanted directions. And then, as we are doing this iteration, the power iteration, at each stage, we would actually look at this vector xk and again remove the unwanted directions. And if we can do that consistently, then we would get a procedure which actually makes this whole trick work. Okay? Let's have a look at it. How do we remove unwanted directions? Key question. Well, we have to use projections. And the projections, you think back to linear algebra again, they are much easier if the vectors have norm 1, Euclidean norm 1. So, there's another assumption. We actually want orthonormal basis, which means that the vectors are perpendicular mutually for I not equal to j, and the Euclidean norm, which is you square the coordinates, sum up, square root, the usual stuff, the Euclidean norm should be 1 for all I. So that's my new assumption. And with this assumption in place, we can do the following trick. When somebody gives us a vector xk, we subtract the projection of this vector to the first coordinate, to the first eigendirection, which is v1. How does this projection work? We have to find the inner product of our vector with this direction, and then this will be a number, and this number essentially describes how much of this vector is in the direction v1, and then we take this and subtract it. So that's the component of vector xk in the direction of v1. And then we of course subtract for the second vector and so on for all the vectors that we already know. So if we know lambda 1 through lambda n, some eigenvalues, each one having some eigenvector, then we are subtracting all the way to xk inner product or dot product vn, vn. So that's an operation that we can do at every stage of our iteration, including the stage 0, when we are just guessing the initial vector. Let's give it a spin. Okay, so I have a code here. See, because we are reaching into the iteration, this should be a part of the iterating step. After we modify, then we do the remaining part of power iteration. We multiply by matrix A, we divide by this approximation of lambda, and so on. So really reaching into the procedure, I have to do it by hand. So here is the first run, with lambda 1 being negative 60, and the eigenvector, if I see it correctly, is 01010. 01010. And O. Okay, so the next step is a check that what we inputted is really the eigenvalue and eigenvector. So we expect to see vector with 5 zeros on the output at this stage. Then I'm normalizing the eigendirection, the vector v1, so that it has norm 1 in a Euclidean norm. Then I set up the initial vector x0, and I'm actually recycling the same vector that I used before for the first run. I'm not adjusting it to be perpendicular to anything, because I know it will be taken care of with this term. I'm going to remove the unwanted directions anyway, so I don't bother here at this initial stage. Here we go, that's my initial vector. And now here this code essentially is just one step of power iteration. So for instance here, you can see the Rayleigh quotient. We are estimating the eigenvalue here. And over here you can see that I take x that I iterate with, and I subtract the projection onto the direction v1. So that's exactly this code, just with v1. Okay, let me run it once. So that's the outcome of the first iteration, and that would be actually the first row if I use the power iteration procedure that I have here. Okay, but I cannot use it. I sort of reached into it. I'm messing up with it. So I run it a few times. Second, third, fourth, fifth, 6, 7, 8, 9, 10. So I ran it 10 times. Do I see some convergence? Perhaps yet. Yeah, okay, let's be on the safe side. Let's run it a few more times. So it seems that we are really getting eigenvalue 36. I can see it there. Nice convergence. And when I look at the vector, eigenvector perhaps, I can see 1, 0, 1, 0, 1. Yeah, that's exactly this guy, the second largest eigenvalue. So the trick with removal seems to work, but now it gets interesting. I have two forbidden directions. Let me input the second one. So the eigenvalue is 36, and the eigenvector is 10101. 10101. And again, I'm going to check that my data is correct, normalize V2, and set up the first iterating vector, the initial one. So it's actually the 0th vector. And now again, I'm going to use power iteration, but this time there will be two projections because I'm removing two directions. And you know what? Let me start with this guy because that was a good attempt. 0, 0, 1, 0, negative 1. Let me start with that one. I could actually start with the initial vector that I'm using always as a default in this example, but let's have a look at this. What happens to this run if I do not let this first two dominant guy interfere with my iteration? So here we go, that's the initial vector. And now let me run the iteration a few times. So we can see here that we should be getting eigenvalue 12, or perhaps not, because there are two competitors now. And when you look at it, the eigenvalue pretends to be 9, but we know that it's nonsense because when we look at the vectors, this is definitely not a convergent situation. In fact, we see a cycle. Okay, so we remember we have a vector which is essentially half, 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 negative 1. And I do two iterations, and we have the same vector. Half, 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 negative 1. We are in a loop. So if I actually shift, everything works the way we expect it. If I shift it, and if I try this by hand, it does seem to work. So this removal trick is really the key to success for this idea with perpendicular initial vectors. However, as you could see, it's a lot of trouble. I could write down a new procedure which does it, but this is too much work. All those projections, all those calculations, too complicated. There is a way to do it in a much more elegant way, but to get there, we need to do some black magic. Let's have a look at it. I take this vector and I just give it a name, temporary name. Let's call it Z or Z. And what I'm going to do, I'm going to have another look at these projections. This expression can be written in a different way, in this way. I take vector v1, I do the usual matrix product. This is the dot product or inner product. This is the usual matrix multiplication with vector v1 transposed. And use this to multiply the vector xk. How do I know that it's the same? I never learned such a thing in my linear algebra classes. This is a very specific formula, but it does work. Let's think about it. What is this animal over here? This is a vector which is a column vector. And we use the usual multiplication, matrix multiplication, to multiply it with transposed column vector, which is a row vector. It looks like that now. What do we get? Well, we are using the matrix multiplication, so we are trying to go by rows, by columns. How many chances there are? Well, there are many possible combinations for our multiplication. We can choose different rows, different columns. In fact, the output of this is an n by n matrix. And you can think of what the entries are. For instance, the upper left entry is obtained by the first row, the first column. This is v1, v1. The second entry in the row is the first row, second column, v1, v2, and so on. So it's possible to work out the terms of this matrix. And now this matrix, this n by n matrix, multiplies a vector, which is a column vector. So it makes sense, and the output is a vector. And this is a vector, so we can subtract. It all makes sense. And when you multiply this matrix by vector xk, x1, x2, and so on, and you check out the output, and you compare it with this, you will see it's the same. Okay? So really these two expressions are the same, although it looks like a black magic. It's actually proper mathematical work. And what's the advantage? You will see in a second. Okay, I'm going to do it everywhere. Vn multiplication Vn transpose xk. One advantage is that now we have two matrix multiplications, so we can drop the bracket. It's just a group of 3 multiplications. And it becomes even more interesting when I take this vector and multiply it from the left by a. Why do I want to do it? Because that's the power iteration. You take your iterate vector, xk, multiply it by a, and divide by the lambda approximation. So let's not bother with lambdas. Let's have a look at az. Well, I'm multiplying by a, vector xk, minus, and now I'm multiplying by a, and that's also a matrix multiplication, so I have to be careful. I cannot rearrange the order. That's forbidden. So a has to come here at the start. A v1, v1 transposed xk, minus, and so on. And this is happening everywhere with all projections. And now here comes the payout, the payoff, the great moment. First of all, I'm going to factor out xk because that xk is just multiplied in the usual vector multiplication from the right at every term, and distributive law works actually. So xk comes out. That's very nice. In the original formula, xk was sort of hidden inside inner products. I wouldn't be able to do that, but now I'm able to pull it out. That's very nice. Okay, let's have a look at this expression. I'm factoring out, and here AV1, V1 is an eigenvector, so AV1 is essentially lambda 1 V1, and then V1 transposed, and so on. Now, does it make sense? V1, V1t is a matrix. We talked about it. So it's a matrix which is multiplied by a number, subtracted from a matrix. This does make sense. This creates a new matrix. And in the same way, I go all the way to the last term. So what we see here is the heart of the power iteration step. You have your vector xk at the start, and in the usual power iteration, you would simply multiply it by a and then divide by lk. Okay? What we do here, we insert this intermediate step with projections, but when we look at the formula, we can see that actually we can store those projections in the matrix. This is a new matrix B. And if I forget about this modification of matrix A, this looks like the usual power iteration because I take the vector xk and I multiply it by a matrix, the new one, matrix B, and then I divide by L and do all the stuff. So the trick is that if you want to use those projections, the removal of unwanted directions, you don't have to do it manually inside your power iteration. Instead, you simply change your matrix. And then you apply the usual power iteration to this B. And that's finally the version which works in applications, which makes sense, which is even convenient because you are just changing the matrix. And this actually has a name. This is called the deflation method. And let's see, it's the last slide for today. So that's usually good news. It's almost over. Let's see, what does it say? It says we have a matrix, we have eigenvalues and eigenvectors, and we assume that the vectors are normalized with respect to the Euclidean norm. Then we set up an auxiliary matrix, B, which is A, and also the projections included. And then we run power iteration, and we obtain the next largest eigenvector, or perhaps there's a tie, then we shift, whatever. Let's not worry about technical details. So that's the deflation method. Now notice that for the eigenvectors, we want them to have norm 1 with respect to the Euclidean norm. Now there is also normalization happening inside the power iteration, and typically we would use the infinity norm. But having two different norms, it doesn't look really good. It's not consistent. It's not a problem, but it's an extra work. If you use Euclidean normalization in power iteration, then the v's which you get out of it, these guys, will already have Euclidean norm 1, and you can directly use them in the deflation trick. So when we go back to our 5 by 5 matrix and try to run this example again, I will actually use normalization with respect to the Euclidean norm. I will do another thing. Let's go back to our code. Here is our matrix A, and we start by running power iteration. And notice, this time I'm using normalization with respect to norm 2. So the output, the eigenvector, should have norm 1 in Euclidean norm. Let's have a look at it. Previously, we got vector almost 0, 1, 0, 1, 0. But this time we don't have 1s, so that the norm is equal to 1 in the maximum norm. But instead, we have something like 0.707 and so on. This is essentially half of the square root of 2, by the way. Something that you have to do so that the norm of the vector has Euclidean norm 1. Okay? But otherwise, negative 60, that's the largest eigenvalue. Everything works. And this brings me actually to the last important point of today's talk. I was worried about numerical errors. That's why we do this removal. How about here? Perpendicular vectors. This is very extremely sensitive to numerical errors because you have two vectors that are perpendicular. Now, if you change one of them, even slightly, even tiny change, they are no longer perpendicular. And that's where the trouble starts because, okay, we have vectors v1, v2, and then we find something, we are removing projections over here, but we are actually not removing true eigenvectors, true eigendirections. Why not? Well, all these problems that I did today, I was actually cheating. These are school problems with really cute answers, integer-valued answers. But in real life, somebody gives you a matrix. And you don't know that the eigenvalues are going to be integer-valued, and you don't know that the eigenvectors will have a nice representation. You are just getting some vectors. You don't know what to do with them. You look at this vector, there are some numbers, and you have to keep them. Because you cannot just make them nicer. You don't know that your matrix has nice answers. So in this run, now that I'm going through this example, I'm actually not going to cheat. I'm going to keep exactly the output that I get from my procedures. So for my lambda, I get negative 60. Okay, I do get. And for my vector v1, I get exactly this animal. And you can see that instead of zeros, there will be 0.1, 2, 3, 4, 5 zeros, 2, 6, 9, something like that, okay? So let's see. I'm keeping the output, and I prepared my new matrix B using the projections. And you can also notice that I commented out the normalization step because my vector is already normalized with respect to the Euclidean norm. And now I'm going to run power iteration with this matrix B, and I keep the initial vector as before, my favorite, okay? Lots of 13s, I love it. And again, I normalize with respect to the Euclidean norm. And let's see what we get. We are getting 36, which is the second largest eigenvalue, so this works. How about the eigenvector? Do I see zeros on the second and fourth position? I essentially see zeros. Do I see ones? I see 1, 1, 1. Well, I see the same numbers. So if I normalize with respect to the maximum norm, I should get 1, 0, 1, 0, 1, 0, 1. So yeah, this is the right direction. Let's store it. Let's store the imperfect versions. This time, my new matrix B is actually A modified with 2 directions. I'm removing 2 unwanted directions. So I know these 2 guys, and I'm asking for the third one. Okay? Let's see. I run this new matrix B with the same initial vector as before, and so on. And I can see that we have a cycle because we are not surprised because we know that there is competition, but even if we didn't know it, we would see it here. There is actually infinite loop. And when I look at, let's say at the 5th coordinate, I can see that every second vector is essentially the same, okay? So yes, we have a loop, we have to shift our matrix. So I'm shifting the matrix slightly. Let's say by -1 to the right. Okay, no problem there. And I get eigenvalue 12, perhaps. And now, how about the eigenvector? I can see that the third coordinate is twice as large as the first or the third, which is exactly the case over here. And there is the opposite sign, okay? So this ratio seems to fit. And I can also see that the second coordinate is halfway, in absolute value, halfway between the first and the third. 3 is halfway between the second and third, okay? So the vector that we see over there should be parallel, should be the same direction as this guy, okay? And you can check if you take this vector and divide it by, well, divide it by the first coordinate and multiply it by 2, and you should get it. Okay, let's play. Before I do it, let me just store the results. So my results are stored as L3 and V3, and I set up a new matrix B, which is essentially, again, I'm removing 3 directions now. I could use the opposite shift if I wanted to get at number 12, negative 12. But I'm following the deflation algorithm. I have 3 vectors, so I'm going to remove them. Now I'm removing also the third direction. Okay, before I get there, let me make an intermediate step. I'm curious. I take the vector v3, I multiply it by 2, and I divide it by the first coordinate. What do I get? And I'm getting vector 2, negative 3, negative 4, 3, 2, essentially. Okay, so my vector, my eigenvector v3, is a good approximation of this direction. Well, not all that good, but it's reasonably close. Okay, so let's run my power iteration again. I'm not shifting anything now. I simply keep my initial vector as before. I take this b, which is now removing 3 directions. It's removing this direction, and this direction. Perhaps I should make a note of it. So this one is gone, this one is gone, and this one is gone. Let's see. Wow, that was short. Let me return to it. Why is it so short? Okay, we are getting negative 12, which seems to work. And we are getting a vector where every entry, apart from the last one, seems to be 1/2, more or less. If I multiply by 2, I get 1, 1, negative 1, negative 1, 0. So again, this seems to be the right direction. So let's ban it. We discovered everything that we knew before, it seems. And now it gets interesting. So I'm going to store this output. I'm going to prepare the last actual matrix. I take A, and I'm removing first direction, second direction, third direction, fourth direction. There is just one direction left, so we should get the result. Let's see. Bang. Okay, we've got eigenvalue 12, an eigenvector that looks, well, that's a good question. How does it look like? Okay, I think that the first coordinate is a triple of the second coordinate, roughly triple. Yeah, it seems like that. And the last coordinate is about 4 times the fourth coordinate. Let me divide this vector. So this vector, let me store it first. It would be v5. So I'm going to store it like that. Is that right? Yeah, it's that right. And now I take v5 and divide it by the second coordinate. And we are getting vector 3, 1, negative 1, negative 1, 4. Is this the eigenvector and 12 the eigenvalue? That's a good question. So let me just check that A times this vector minus 12 times this vector should yield 0. Is it true? Yeah, essentially yes. We are getting essentially zeros. So really, negative 3, 1, negative 1, negative 1, 4 is an eigenvector, and it's a different direction from this one, which shows that 12 is actually eigenvalue of multiplicity 2. Finally, we found the answer. Finally, we know everything. So here for 12, I'm actually adding another eigenvector. Let me change the sign so that I start positive. It's always good to start positive. Negative 1, 1, 1, negative 4. Here we are. So we know the complete list of eigenvalues with their eigenvectors. Everything is wonderful. Let's return back to the question of runs. Okay? This last run was fairly short because there was essentially just one direction left. So the iteration just needed time to find it. And it found it fairly easily. The second last run, this one is suspicious. Let me go back to it. Why is it suspicious? Well, let's think back. What does it mean, the third run? The third run worked like that. We removed this direction. We removed this direction. We removed this direction. And now we are running the auxiliary matrix. What were the eigenvalues? Well, we removed this direction, but now we know that there was another 12 appearing still in the game. And there is also negative 12. So how come that we didn't get an infinite loop? That's what we would expect, actually. Now that we know all the information, we know that 12 is there twice. If you remove one of them, the second guy is left in the game. Why didn't we get a tie? Instead, we got very quick result reading negative 2. And the answer is we got extremely lucky. Sometimes you do get extremely lucky. The very first direction that we got, after it got multiplied by matrix A, then accidentally, we already got the eigenvector. So this was algebraic luck, extreme algebraic luck, because the chances of this happening are almost nil. And because the procedure found the eigenvector for negative 12, it stuck with it. And it said, oh yeah, I got it. So we were really lucky. If we were not this lucky, if I change the initial vector just a little bit, how about if I change the last coordinate to something random, like 13? Yeah, totally random vector. So this time we will not be that lucky. You cannot get this lucky twice. So if I multiply this new initial vector by A, I'm pretty sure, almost sure, that we do not get eigendirection out of it. And that's why the iteration will have some room to play. It will discover that there are two competitors for the largest eigenvalue. I expect to see a loop, infinite loop. And I do. Okay. When we look at the last coordinate, we can see that every second vector is the same. So yeah, things behave as advertised, which is wonderful. So much for this remark. Let's go back to the example. What did we just see? We saw deflation method in the efficient way implemented by changing the matrix. And it worked like a charm. It took our 5 by 5 matrix and it found all the eigenvalues, all the eigenvectors. Even though one eigenvalue was of higher multiplicity, the procedure found everything. It did even survive that we didn't cheat. We didn't round these answers to something nice. We used it as it came from the procedure. So we used approximate eigenvalues, approximate eigenvectors. The procedure still handled it beautifully. So this is a very robust procedure, deflation, wonderful. Let me show it again. Let me part with it like that. Okay, so the deflation procedure, that's the happy end. It doesn't get any better in this course, so this is the best time to stop. Hope you enjoyed it as much as I did. And see you next time. So let's try this iteration, the one that we have here. It's called power. I'm getting tired. Okay. This one is really getting to me. Okay. I will do it now. But this guy is perpendicular to my starting vector. I didn't write it down. I'm a moron. That's the happy end. It doesn't get any better, so this is the best time to stop. Hope you enjoyed it as much as I did. And see you next time. Did I forget something? Anything? Let's see. I said this. Okay. I guess I said it all. We are done. Okay.